Taking on the concept of the first derivative test, I would like to get back to this case. So let's say there is a function f which is defined in an interval I, and we want to find out possible local maximum points for this function, or we want to find out possible local minimum points for this function. And if we want to do that, we would like to search among these types of points. We would like to take up interior points in I where f prime x is equal to 0. We would like to take up the end points in I. We would like to take up points in I where f prime does not exist. But we know that we just cannot calculate the function value at all these different points, and that's not going to help us determine possible local maximum points or possible local minimum points, because as I have already explained, this is a global optimization procedure. For the local maximum point or the local minimum point, this kind of procedure is not going to help us. So now what we do is we take up the first derivative test, wherein we consider a differentiable function, and let us say we know that there is a differentiable function and we are concerned about local extreme point in the interior of the domain of that differentiable function. And we are going to, in that case, obviously I know if there is an interior point, in the domain of a differentiable function, and we know that that interior point, it is a stationary point. So I know that it is a local extreme point, and if it is an interior point in the domain of a differentiable function, that means obviously the first derivative has to be 0. So that is nothing but a stationary point. We would now like to know when is that stationary point a local minimum, when is that stationary point a local maximum, or when is that stationary point neither a local minimum nor a local maximum. As what we have already seen, that we just cannot calculate the function values at all stationary points and get to the maximum or the minimum out of those. That's not what we are going to do. So what is the procedure that we have to follow in order to determine whether the stationary point we have is a local maximum, is a local minimum, or neither? So for that we take the first derivative test. So this is the first derivative test I should write for local extrema. And here let's suppose C is a stationary point for y is equal to f of x. So it is a stationary point, and we have a differentiable function f. Let's say C is a stationary point for this function. That means the first derivative at this point is equal to 0. Now we take up 3 cases. The first point to note here is that if f prime x is greater than equal to 0 through some interval a to c to the left of c. So there is an interval to the left of c, AC, it's an open interval, and in this interval f prime x is greater than equal to 0, and f prime x is less than equal to 0 through some interval, in fact I should say throughout. So instead of this, throughout some interval, and here also throughout some interval, this to the right of c. Then x is equal to c is a local. Now what we see here is that f prime x is greater than equal to 0 through some interval a to c to the left of c, and it is less than equal to 0 throughout some interval c to b to the right of c. Sorry, I should have said throughout earlier. It is less than equal to 0 throughout some interval c to b to the right of c. Then what I mean to say here is that the function is increasing to the left of c, it is decreasing to the right of c. That just means that x is equal to c, and I know that c is a stationary point. That means f prime x is, I know that f prime x is equal to 0 at c. So f prime c is equal to 0. If I say that suppose c is a stationary point for y is equal to f of x, that just means this: f prime c is equal to 0. So now I see that the function is increasing to the left of c, it is decreasing to the right of c, and c is a stationary point. That is the tangent to the graph of the function. The slope of that tangent is 0, or the tangent to the graph of the function at point c is parallel to the x-axis. The function is increasing to the left and the function is decreasing to the right. In an interval to the left it is increasing, in an interval to the right it is decreasing. That just means that x is equal to c is a local maximum point for f. It is a local maximum point for f. Second thing to note here is that if f prime x is less than equal to 0 throughout some interval a to c to the left of c, so now it's the other way. The function is decreasing to the left of c, and f prime x is greater than equal to 0 throughout some interval c to b to the right of c. So the function is decreasing. So the function is decreasing to the left, it is increasing to the right. That means, and I know that that point c is a stationary point. So the tangent to the graph of the function at that point is parallel to the x-axis. The function is decreasing to the left, it is increasing to the right. That just means that that point x is equal to c is a local minimum point for f. Then x is equal to c is a local minimum point for f. Now the next point, the third thing to note here is that let's say f prime x is greater than 0 both throughout some interval a to c to the left of c and throughout some interval c to b to the right of c. That just means that the function is strictly increasing both to the left of C and to the right of C. At C, I know that the tangent to the graph of the function at C, I know it is parallel to the x-axis. So f prime C is equal to 0. But the function is strictly increasing both to the left of C and to the right of C. Then x is equal to C is not a local extreme point for f. And the same thing holds if my function is strictly decreasing on both sides of C. So the point to note here is that if the function is strictly increasing on both sides of C, given the fact that C is a stationary point for that function, but the function is strictly increasing on both sides of C, or if the function is strictly decreasing on both sides of C, then x is equal to C is neither a local maximum nor a local minimum. That means that x is equal to C in that particular case is not a local extreme point for f. So I can say that if f prime x is greater than 0, or I can just write it like this, both throughout some interval a to C to the left of C and throughout some interval C to B to the right of C. Then x is equal to C is not a local extreme point. That means neither a local maximum nor a local minimum for f. Let's now take up two questions. Before I take up those two questions, there is one point to note, and that is this. So let's say f prime x is greater than 0 in a to C and this. This implies f of x is strictly increasing in a to C like this and in this. So what is the difference here? I'm saying f prime x is greater than 0 in a to C, a and C not including. So C is not a part of this interval, but any point to the left of C, or that point can be as close to C as possible, but it is not equal to C. What we are trying to understand here is that any point to the left of C, the function is strictly increasing, and any point, and at C I know that the function is stationary, or the tangent to the graph of that function is parallel to the x-axis. That just means that even if I include C, the function is strictly increasing in this case. Also, if the function is strictly increasing here, that means any point to the right of C and till B, we know that the function is strictly increasing. At C, the tangent to the graph of the function is parallel to the x-axis. That just means that we can again take up the function being strictly increasing in this, because of the fact that at C, in this case and in this case, the function is stationary. Okay, to the left of it the function is increasing, to the right of it the function is increasing. That means we can include C, and at C the function is stationary. So we can include C, and we can say that A to C is C inclusive, the function is strictly increasing. C to B, C inclusive, the function is strictly increasing. And that just means if we are including C here, obviously this implies that x is equal to C. Even though it is a stationary point, it cannot be a local extreme point, because we are including C, and what we see here, we are including C, and to the right of it and to the left of it the function is strictly increasing. So that just means that x is equal to C cannot be a local extreme point. Now let's take up a question. The question is that we would like to classify, so the question is classify the stationary points of f of x is equal to 1 by 9 x cubed minus 1 by 6 x squared minus 2 by 3x plus 1. We have to classify the stationary points of this f of x, 1 by 9 x cubed minus 1 by 6 x squared minus 2 by 3x plus 1. So basically we have to take up the stationary points, and when I say classify, that just means we have to see which of the stationary points are a local maximum, which of these are a local minimum, and which of these are neither. So for that we first calculate f prime x, which is equal to, so I think we have done this earlier also, and there f prime x turned out to be this. In this case it's exactly the same question we have considered earlier, 1 by 3x plus 1 minus x minus 2. So we can now take up, so this is f prime x, and we can think of the sign diagram here. We have, when we take up the sign diagram, we can just think of it this way, that we first take up this, then we take up this, and then we take up their product. So if I take up 1 by 3x plus 1, it is, I know that it is greater than equal to 0 when x is greater than equal to minus 1. So let me take up the sign diagram now. Here, this is the sign diagram for f prime x. My f prime x is equal to 1 by 3 x plus 1 x minus 2. And as I said, I have to first take up 1 by 3x plus 1, which is, you can see that it is greater than 0 here. It's the bold line, and it is less than 0 here. It's the dotted line. And then we have x minus 2. So x minus 2 is greater than equal to 0 for x greater than equal to 2. And that means we see that, here we have this dotted line, not dotted line, the bold line after 2, and the dotted line before that. So that's the case. And if we take up their product, and that just means that in this case you see that here you have positive, here it is positive. So if I take up f prime x, which is their product, so this will be positive here, and it's negative here, so it's positive here. It's positive and negative, so it's negative. So this is negative, this is positive, and this is positive. If f prime x is positive here and negative here, that just means I know that the stationary points here are x is equal to -1, x is equal to 2. And clearly I see that before that, before x min, or I should say to the left of x is equal to -1, to the left of -1, I see that the function is increasing. To the right of it, the function is decreasing. So that's why it's like this. And that means this is a local maximum point. If I take up x is equal to 2, I see that the function is decreasing before this and it is increasing after x is equal to 2. X is equal to 2 is a stationary point. At that point, the function is stationary. So obviously that means x is equal to 2. This is, so that means, and clearly we see that it's decreasing then increasing, so 2 is a local minimum point. So what we see here, that x is equal to -1, it is a local maximum point, and x is equal to 2, it is a local minimum point. So that's how we have classified the stationary points of f of x. The stationary points are x is equal to -1 and x is equal to 2. We have now classified them. So x is equal to -1 is the local maximum point, x is equal to 2 is the local minimum point. We have applied the first derivative test. We have taken the help of the sign of the first derivative to the left of the stationary point to the right of the stationary point, and that's how we have deduced whether our stationary point is a local maximum or it is a local minimum or it is neither. In this case, where we have two stationary points, one turns out to be a local maximum point, the other turns out to be a local minimum point. So let me just write that x is equal to -1, x is equal to 2, -1, that's a local maximum point, and this is a local minimum point. I now take up another question. So again, we would like to classify the stationary points of f of x equal to 6x cubed divided by x raised to the power 4 plus x squared plus 2. Now in this case, if we take a look at this, I know that if obviously we have to first think of the domain of this function. That's the first step always. Now I know that if I look at the denominator, it is greater than equal to 2. It is x raised to the power 4 plus x raised to the power 2. So obviously in this case these two will be greater than equal to 0, and that just means that the denominator is greater than equal to 2 for all x. So my denominator will never be 0, and that means I can't say that f of x is not defined for such and such x. So in fact f of x is defined for all x. That's something we are clear about. What we now do is that we differentiate f of x with respect to x. So we take up f prime x, and if I take up f prime x, that leads to, that we can do with the help of the product rule, and that is equal to x raised to the power 4 plus x squared plus 2 whole squared, and I just now write x raised to the power 4 plus x squared plus 2, and then this is 18x squared minus 6x cubed. Then I differentiate this minus the numerator, then the derivative of the denominator. So it's 4x cubed plus 2x. If I calculate this leads to, so I have 18x raised to the power 6, 18x raised to the power 6, then I have 18x raised to the power 4 plus 36x squared, then it is minus 24 x raised to the power 6, then it is minus 12 x raised to the power 4 then I divide it by this same thing. This is then equal to, so it's minus 24 plus 18, so it's minus 6x raised to the power 6. 18 minus 12 is 6, x raised to the power 4 plus 36 x squared. So we have this now, and this is equal to minus 6x squared. We can just take that out, and if we take it out, we have x raised to the power 4 minus x raised to the power 2, then it is minus, and then it is 6. So that gives us x raised to the power 4. Okay, now that's like the same thing. So we need to now actually factorize the numerator, and for that what we have to do is, in fact I think I should say we should factorize x raised to the power 4 minus x squared minus 6. That's what we have to do, because we have to kind of study the sign variation of f prime x, and we have to classify the stationary points of this function. So for that what we have to do is we have to factorize x raised to the power 4 minus x squared minus 6, and that's what I do separately here. X raised to the power 4 minus x squared minus 6. So this can then be written as this minus x squared minus 6, which can then be written as now what I can do is I can put x squared as y, and if I put x squared is equal to y, so I have y squared minus y minus 6, that is equal to y minus 3 y plus 2, and that means I can now write this as x squared minus 3 x squared plus 2, and this can then be written as root x plus 3 root x minus 3 multiplied by x squared plus 2. And now in this case I can now just get back to my f prime x, and write exactly what my f prime x is, and that is going to actually give me f prime x equal to minus 6x squared, and then instead of this expression I can now write this expression. I can write this x minus root 3 x plus root 3 x squared plus 2 divided by x4 plus x squared plus 2 raised to the power 2. Now if we take a look at these two expressions, this and this, the denominator and this factor in the numerator, which is x squared plus 2, these are always positive, so we don't have to worry about these. And that means if we have to take a look at how f prime varies, we have to be focused on the other factors in the numerator. As in, if we want to take up the sign, we want to study the sign variation of f prime x, we would actually be focused on the other factors in the numerator. And that's exactly what we do, and that's how we take the first derivative test. So for taking the first derivative test, we are going to ignore x squared plus 2, and I'm obviously going to ignore the denominator because both of these are always positive. I'm going to be focused on this. So first I take up minus 6x squared, then I take up this, and then I take up this, and then I take their product, and that's how I study the sign variation of f prime x with the help of a sign diagram. So this is the sign diagram I have, and if you can recall, I had to study minus 6x squared, x minus root 3, x plus root 3. That's how I would like to study the sign variation of f prime x. For that, if I take a look at minus 6x squared, so I hope everyone is clear about this fact that this expression is this expression in this, I mean, if we take a look at this expression minus 6x squared, this expression is equal to 0 when x is equal to 0. And this expression, come what may, whatever x is either positive or x is negative. Whatever x is, this expression is always, obviously let's not get into x being 0. Apart from x being 0, this expression is always negative because we have x squared. So x squared is greater than equal to 0. That just means minus 6x squared is always less than equal to 0. So that is why it is minus in this way. So it's minus everywhere. And if we take a look at x minus root 3, I know if I think of x minus root 3, when is it greater than equal to 0? When x is greater than equal to root 3. When is it greater than 0? When x is greater than root 3. So that means we see that here it is positive. When x is less than root 3, it's all negative. If we take up x plus root 3, we know that it's positive when x is greater than minus 3, that when x is greater than minus root 3. So we see that it's positive here, and here it is negative. Now we have to study the sign variation of f prime x. For that we have to only take up, we only have to be focused on these three factors. So we know that it's minus minus minus, so minus is multiplied by minus and then multiplied by minus, so it's a minus here, and it's a minus minus which is plus, then plus, so it's a plus here, again minus minus plus, and a plus which is plus here, so minus plus plus, that means it's a minus here. So we know, looking at uh, those those three expressions which we have to be focused on, minus 6x squared, x minus root 3, in fact it is this. So it is, let me just write it like this. So it's minus 6x squared, x minus root 3, x plus root 3, x squared plus 2 divided by x4 plus x squared plus 2 squared. When is this equal to 0? When x is equal to 0, x is equal to root 3, x is equal to minus root 3. So these are the three stationary points. And what we see here, if you take a look at minus root 3 first. So before minus root 3, as in to the left of minus root 3, we see that the function f prime x is negative. That means the function is decreasing. So what we see here is that the function is, it's going down before that and it's going up after this. So it's like this. And that means x is equal to minus root 3. It's a local minimum. It's a local minimum point. X is equal to 0. I see that f prime x is greater than 0. To the left of 0, it is greater than 0 to the right of 0. That means x is equal to 0 is neither a local maximum nor a local minimum point. It's neither a local maximum point nor a local minimum point, because I see that f prime x is greater than 0 in minus root 3 0 and 0 root 3. We see that here f prime x is greater than 0. That just means x is equal to 0. Even though it is a stationary point, it's not a local extreme point. X is equal to minus root 3 is a stationary point, and we see that it is a local minimum point. If I take up x is equal to root 3, I see that the function is decreasing. It is increasing to the left, decreasing to the right. That means x is equal to root 3. It is a local maximum point. So that's how we have classified the stationary points of this function. So stationary points here are x is equal to 0, x is equal to minus root 3, x is equal to root 3. 0, not a local extreme point. X is equal to minus root 3, it is a local minimum point. X is equal to root 3, it is a local maximum point. Now, if we take up the diagram of this, if we take up the graph of this function, we can see this. So this is the graph of this function, and you can see here that there are three stationary points. X is equal to 0, then it is x is equal to minus root 3, then it is x is equal to plus root 3, and it is this, so, and it's this. So clearly we see, so that's root 3 and that may be minus root 3 and that is 0, and we can see here that x is equal to minus root 3 is a local minimum point, x is equal to root 3 is a local maximum point, x is equal to 0 is neither a local maximum point nor a local minimum point.